All right, and we are live. Um, a warm welcome to everybody to the 16th live stream of Engineering Trainer TV, live here from the Engineering Trainer studio in the Netherlands. My name is Luuk Hennen. I'm the CEO and one of the founders of EngineeringTrainer.com. And today we are going to have a conversation with Mick Bouman, who is a project engineer at Dynaflow Research Group, and who we are going to talk with about the topic of Waterhammer in industrial piping systems. Mick, it's a pleasure to have you on board. How is your day going so far?
Thank you very much. Thank you very much. Yeah, my day is going quite busy, as the life of a project engineer is, with many projects going on and supervisioning of the engineers at Dynaflow. But things are going good. Thank you.
Busy as it should be.
Yeah.
Appreciate you making the time. We've chatted before and always had great conversations. So it's great to have you on board of the Engineering Trainer live streams. Now, Mick, before we dive into the actual topic, let me also welcome everybody who is watching this live stream and invite everybody to join the chat. Everybody who is tuning in remotely, welcome, and please ask questions in the chat. Join there, provide comments, share your thoughts on the matters that are being discussed. And as always, in our live streams, I'm asking you, everybody who is joining remotely, to share in the chat from where in the world you are tuned in. It's always great for us to see, the different locations around the world where people are tuning in from. So please make sure to open the YouTube chat as we speak. Drop in your location, and by that way, you also have the chat open if you have any questions or comments. I also invite everybody to follow Engineering Trainer on LinkedIn or on YouTube, which are two great ways to stay up to date about any of our activities. The same holds for Dynaflow Research Group. Make sure to check out their channels as well. And as a final note, I would like to say that everybody who's tuning in will receive a nice discount coupon to join the course on Engineering Trainer as well. And you can find the link in the show notes of the video in YouTube, where you have to click on, fill in your email, and then you'll have it in your inbox in no time. Now we have several courses on Engineering Trainer related to today's topic, for those who want to expand their know-how after this stream. And I'll briefly share my screen later on at the end of the stream and walk you through some of those courses. We're aiming for the stream, roughly 45 minutes. We might go a bit faster or stretch it a bit out a bit longer, depending on any questions that we might get in the chat and how the conversation goes. All right. So Mick, let's just start with you. From where are you tuning in today?
At the moment, I'm at the Rijswijk office in the Netherlands. And we have a special training room here that we have created for these kind of settings, and also for online trainings and stuff like that. So
Awesome.
especially during the past 4 years, that was quite important, of course. But nowadays we see a bit more classroom training. But we can still properly use this room.
Yeah. Nice, from like tuning in from the Dynaflow studio, so to speak, in the Rijswijk, the Netherlands.
You see the branding on the rooms here, on the windows.
Yeah. We should, over time, I think we should have something similar, like mount something to the wall here,
a
like
big sticker.
Yeah, a big sticker, exactly. Hey, Mick, you have well over 14 years of experience as an engineer and consultant at Dynaflow.
Yeah, true.
You have led, numerous of projects, of which many also focus on addressing Waterhammer challenges.
Yeah.
And we actually worked on some projects together related to Waterhammer mitigations in the past.
Yeah, back in the days.
Back in the days, exactly. Maybe you can kick things off a little bit by sharing what you like about doing a Waterhammer analysis.
Yeah, sure. Well, so in the past, I studied aerospace engineering, where I learned quite a bit about aerodynamics and also how the math works behind doing these kind of calculations. And what I like about Waterhammer is that the theory behind it is quite mathematical, but the implications of that can be understood quite easily, and you can
Hmm.
get quite a sharp intuition for what's going to happen in a piping system.
Hmm.
And yeah, now we have really cool tools in order how to calculate the effects of Waterhammer. Um, but yeah, the combination of having an intuition, being able to more or less predict what is qualitatively going to happen, and that you can then use a tool to quantitatively,
Yeah.
yeah, say, assess what's going to happen. And there are certain things like CFD where, yeah, it's really hard to predict how a specific thing is going to look like. But for a Waterhammer study, yeah, quite often you can use your intuition in the whole process, and I like that
Yeah.
part a lot.
Yeah.
Yeah,
Yeah, so a good combination of intuition and the analytics, backing it up and
yeah,
being able
proper
to link
tooling.
those. Yeah,
Yeah.
and out of the project that you did, what are typically the most interesting types of analysis you feel?
Well, what is usually quite cool is when, well, it's not cool for the user, but if a thing fails, doing a root cause failure study, there you really have to use your intuition. Like, okay, apparently they have done an analysis, but maybe in this time something else happened. Yeah, you have to create some hypotheses, and then you can study those hypotheses in a program with which you can study, you say, Waterhammer. So we use BOSfluids for that, but you can use any type of software package.
Yeah,
So, but the idea of forming hypotheses and then checking those, and usually being able to figure out what has happened, maybe in a combination with stress analysis too. But yeah, those kind of projects I quite like. Yeah,
yeah, yeah.
yeah, because they're always challenging.
Yeah. Have you ever? I mean, we're gonna go into details about what Waterhammer exactly is,
Yeah,
how it comes into play, etc. Have you ever seen anything related to Waterhammer happen? I mean, obviously, if a failure happens, you're not there,
yeah,
hopefully, and in your role, you're not typically there as a maintenance engineer or anything. But
yeah.
did you ever encounter or see anything related to Waterhammer physically happen?
Yeah, so quite often things that run in pipes can be dangerous, right, or toxic to people. So luckily, I haven't been close to a real failure, but I have been close to well, testing of various systems where you could hear the effect of Waterhammer. So it was
Mm,
there. It didn't lead to a failure, but for instance, yeah, testing of fire water lines where you start out with a dry system and you open a valve somewhere and the
yeah,
water starts running to sprinkler systems. If you close those systems, yeah, you quite often hear some hammering in the piping. I've had some experience with yeah, yeah, the actual event too.
yeah,
And it was
yeah,
usually an idea then to at least notify the client, like, what you're hearing now is Waterhammer. I hope that you have actually checked
yeah.
what is going on here.
Yeah,
Yeah.
yeah, yeah, yeah. And like those are valve closures or also the filling of lines.
The filling of lines too, that can be, yeah, quite a dangerous thing actually, that people don't consider
Yeah,
usually because it's hard to consider actually. But the things that I was referring to was actually due to closure of lines.
right.
Yeah, yeah. So, but we're going to talk a little bit on that later too, in the
Yeah,
presentation that I have prepared.
yeah, yeah,
Yeah,
definitely. So for today's conversation, Mick, we decided to zoom in a little bit on Waterhammer risks during ship offloading.
yeah,
Maybe we can switch to the scene where we see Mick's screen. And you can just maybe introduce, what offloading even is, and the system, how it is organized, and we can take it from there.
yeah, sure. Yeah, we need to apply a bit of yeah, concentration or to focus on one topic because there is many types of process piping systems where you could experience Waterhammer. So yeah, in this case, we're going to explain Waterhammer for a ship offloading line. well, what is ship offloading? Usually in the chemical industry, say products are made and they're quite often in liquid form. They're quite often stored in liquid form because that's the most efficient. Yeah, so if you have gases, you want to cool them down to a point where they become a liquid, and then you can store them efficiently. So
LNG, yeah.
LNG, for instance, ammonia is a typical, it's a typical product that is being produced and then stored at really cold temperatures. Say general hydrocarbons, they are usually in a liquid form like naphtha. So what you see now on the screen is a couple of tanks, and all these tanks they have piping, say, running through them. So they come from, think that this is actually more like a transfer place, but they could be fed from a kind of production plant. But there's also piping here to transport it to a ship. And what you see here, which is very small, but that is a loading arm that you can connect to a ship. But we're going to show that a bit later. And yeah, if you have a question.
Like I know it's used for, I think, what I was involved in the past was bunkering. So the loading of ships, if I recall correctly. But it's often also used for offloading. I would guess, right?
True. So if you have, so you have tanks which are used for trading, so that's also quite often used, or there are products that are being used on a plant. Then you first have to load them from a ship to your shoreside tank. So for instance, LNG, it is produced in America. We have a couple of say LNG receiving stations in the north of Holland, which were recently built. And they have to receive the LNG, and they make say gaseous form at those locations in order for us to use in Holland. And there the offloading is an important it's an important scenario. Because it only goes one way.
Yeah, exactly. And what are typical lengths? In process piping, everything looks way more compact.
And you go from a pump to a vessel to something else. And within a process plant, it is more common to have lines which are 100 meter maybe, or perhaps even less if things can be placed close together. But here you will see, typically multiple kilometers of say of length. So you see, for instance, in the back, these are huge storage tanks. They might well be connected to these the loading arms over there. So indeed, it's in multiple kilometers, and as we'll see later, that increases actually the likelihood of Waterhammer problems.
Maybe that's a good bridge. Maybe you can zoom in to this. I know on the next slide, we have the model of it itself. Maybe you can elaborate a little bit on that one. And also, after that, let's zoom in a little bit on what Hammer even is, and we can take it from there.
Sure. So what you see here is a real geometrical model of a piping system. This is the way how we model piping systems at Dynaflow Research Group, and that is because we also deal with stresses in piping. So we like to have a real geometrical model, but there are also people who are a bit more process oriented, and they are mainly interested in just the piping lengths and the resistances and maybe some elevations. And they model it a bit more as if it were a process and instrumentation diagram, so PNID, something like that. But we have geometrical models, and we think it helps us in defining the loads that you will see on a piping system that you can use in your stress analysis. And so that's the main reason. Plus I like it also a bit more, actually.
So this is BOSfluids, if I'm not mistaken, right?
This is a BOSfluids model. It looks a bit like a stress analysis model, actually, as you would typically see.
With the geometry in there.
So what you see here, there is a tank, there's a series of pumps, and then there is a typical, say transport line, which has a couple of expansion loops. It has a bridge crossing here somewhere. Maybe there is a road, then
Yeah.
there is another road, so the piping has to cross over those, and you really have to model those as well, as we will see later.
Yeah.
And then there's usually a couple of valves that you need in order to limit the flow, or to at least stop it or block it. Here is the K, or the key, as
Yeah.
a strange pronunciation. And then there is the ship connection usually. And here there's usually a couple of loading arms. And these loading arms, they're quite high structures with some rotating swivel connections in order
Yeah.
for them to be able to move with the ship, because the ship is not a static, say a static connection, right?
Yeah.
There may be waves, there may be the movements of the tides and stuff like that. So they
Yeah.
need to be followed with the use of loading arm.
Yeah. Yeah. Maybe we can just jump there. I know we have one visual of that, just to help the people understand a little bit what the exact equipment is before heading
Of
back
the loading
into.
arm. Yeah,
Yeah. Yeah. I
yeah.
think that could be a
Okay,
nice.
sure. Yeah.
Uh,
So let me then have to skip a couple of slides. So here
yeah. Next one.
are,
This is the one. Yeah.
yeah. So this is the one. So what you see here in the left image on the right side, there is a very big ship. This
Yeah.
is used for transport. Don't know what exactly it is, but it could actually be that this is LNG ship. Here there are multiple loading arms which are connected, and
It's always multiple, right? I've never seen just one.
it can also be one.
Hmm.
It can also be one. It depends a little bit on the available piping actually onshore. So I
Ah,
know
right.
of some ammonia lines who typically have only one of the loading arms.
All right.
Here there's a couple of pumps on the ship, because you cannot pull from the ship, you have to pump it.
Hmm.
And they push the product into the loading arm, say onto the piping, which is going onshore towards the tank.
Why
Due
can't you
to the
pull? I mean, I saw in the model that you just showed that the pump was all the way at the tank side, which was already, something I found remarkable, but
yeah
interesting. And now you say like for the offloading part, the pump is on the ship side.
yeah
Why is that organized like that?
yeah. So what you see here in this image is that usually these lines, they can be used in two directions, right?
Yeah.
You can either receive from the ship or pump to the ship. And in this case, there's also a series of pumps which can pump from the tank into the ship.
Mm.
If you want to turn it around, you just close, say, a series of valves, and you dump into the tank from the top.
Yeah.
That is the reason
Why
for
not use the same
for
pump to pull?
if you start pulling on the line, you get really low pressures, and that can
Yeah.
actually be an issue, which we will show as well later.
Yeah. Yeah.
And
Yeah.
so you will get also cavitation inside the pump, and that's going to damage your pump if you're going to manage at all. So it's better to
Mm.
always push. Yeah.
Yeah, like the discharge side, the high pressure side of the pump, to keep the pressures high.
Yeah. Yeah.
Um, I mean, you already mentioned, why it can happen. You mentioned the boat moves, the boat swivels, the boat drifts off. Do you have any clue about the margins? I mean, I can imagine that they would be able. I have no clue about ships, and I have no expertise in that at all. Do you have any idea? I mean, the boat wouldn't just drift off, right? I mean, they would be able to keep it there. It's probably just like movements, wave movements of the ship, or is it also like really actually like drifting off of the entire boat?
Drifting off, indeed. It is a risk. So you have mooring lines and stuff like that. So in principle, they should be fixed. But it isn't 100% certain. So you have to be prepared of the risk of the boat
Yeah,
drifting off.
yeah,
It's
fair enough.
maybe it is a captain who is not really, or maybe a
Or
younger,
cable
lower rank
breaks.
cable break, something like that. So you have to be prepared, and you cannot make the risk, because if it were to happen, you would just tore off all your pipes, and you can have a major catastrophe. So yeah,
Yeah.
it is an issue. But we're going to show how to protect against that.
Yeah. Do you have any clue about the margins? Like,
how quickly you have to be able to respond, you mean?
yeah, like that loading arm, how far would it stretch?
Yeah, that's a couple of meters. So yeah, we can look at the loading arm. When we go to a couple of slides here further, you will see that in the highest extension, these 2 points, so the point here and the point there, they can be almost say at each other's location in the same location. It can drift off. Well, these things, they may be even about 10 meters long. So it could be even 20 meters extension. You wouldn't want to risk that, but you see that there is quite a bit of horizontal movement possible before it would actually break off.
Yeah. Yeah. Hey, now I know with Waterhammer, you know, the experience I have was very much focused on valves. Maybe we can go one slide back, Mick, and zoom in on what Waterhammer actually is. Maybe some basic explanation from your side.
Yeah, sure. Yeah. So, you start out always with kind of initial condition, and we're gonna explain Waterhammer from the initial condition where you have a kind of flow rate. Typically in a piping system, you will see that you have a flow rate of about 3 meters per second, maybe during the offloading, because you want to get your product as quickly as you can into a ship, because the longer it is in your ship or it's at the quay, the more money it will take, right? Because the whole crew has to be there.
Time is
Everything
money.
takes indeed, time is money. So the quicker the better, but the quicker the higher the risk as well. So there is a benefit or there's a cost benefit there. So, but typically you have flow rates of about 3 meters a second. And what happens when you try to close the valve? The flow actually wants to keep on moving because it is moving. It is also
Momentum.
being that, and it's being pushed actually by the pump. So there's a couple of mechanisms, and but usually if this is a very long line, you try to stop all that mass. And the mass, if you want to stop it in a given amount of time, you need to accelerate it, or actually decelerate it, and you want to stop it, and you need a force for that. And that force is the pressure that you get at the valve. So the pressure is actually stopping the flow. And the quicker you close the valve, the higher the pressure is going to get. And there is then also a limit to how high the pressure is able to go, but we can talk about that a bit later. But in principle, you stop the flow and you need the pressure for that, and that's the basis for Waterhammer. There's another thing is that the pressure information cannot travel infinitely fast. So you get, if you were to stop or if you were to close your valve in an instant, you would stop the liquid, and then you would have a wave of pressure, which is traveling upstream. You would also have a wave of pressure which is traveling here downstream.
How fast would it go? I mean, obviously not infinitely fast. Like what are typical numbers?
About 1 kilometer per second.
Okay.
So if you were to close your valve in an instant, in a single millisecond, then you would only notice the stopping valve at the tank, which is about 2 kilometers away, 2 seconds later. And for that whole time, the liquid is actually going to continue.
Still pushing or pulling. Yeah. All right. Hey, and this valve, where would it be in the system? So, like, what are the two locations most relevant regarding to this valve?
Yeah, the thing is, it can be in multiple locations. It depends also a bit on the plot in which they have created a system like this.
All right.
If you're an owner of the tanks, you want to have a valve that is on your own plot as well, because you can
Yeah.
always go there, you can maintain it, you don't need permits from other people. So uh, there is a preferable location, but it's not always clear that the valve is in the optimal location. That also makes each system different.
All
So, but
right.
in our case, we're going to see that we have a closing valve in the loading arm too.
Yeah.
So, but there could be actually multiple valves that are going to be operated at the same time.
Yeah. Is there, if you would look back at the model that you just showed, Mick, is
Yeah,
there a place where you say like for ship offloading, ideally you would have it here, I guess as close to the pump as possible. I'm just thinking out loud now,
yeah,
yeah.
yeah. Well, that is going to generate the highest pressure probably in the line. However, there's also some other types of phenomena that could occur, and that is cavitation, which we're
Yeah.
going to discuss later too. So actually here it is quite difficult. The optimal would be to have many valves throughout your
Yeah.
system that can stop the flow, bit by bit at the same time. That would be
Simultaneously. Yeah.
super expensive, but that would be the most safe thing to have actually. So, but that is not
Yeah.
feasible. Yeah, of
Yeah.
course.
Yeah.
Yeah.
Hey, and I know when we were prepping, our conversation of today, the term PERC, PERC came up quite often, powered emergency release coupling.
Yeah.
Where would that be located, and how does that relate to the valve that we've been discussing?
Yeah. So usually the perk that is located here in the loading arm
In the arm,
at
yeah.
the coupling with the ship. So what the perk it consists of is two valves, typically ball valves,
Yeah.
that can close fairly rapidly in a couple of seconds, 3, 4, 5 seconds, something like that.
Yeah.
Because if the ship is drifting off, maybe even somebody turns on a motor, then it can go pretty rapidly.
Yeah.
And you need it to close in a low amount of time.
Yeah.
And we have a movie of that, so perhaps we can show
Show it. Yeah.
that movie.
Yeah. Maybe
Yeah,
before you show it, let me just summarize this real quick. So we've got a ship offloading its liquid into those tanks. We've got long pipelines connecting in between. We've got a valve in the loading arm that it needs to close if the ship drifts off. If the margins of that loading arm gets utilized by the ship drifting off. And what this video shows is basically exactly that, like that scenario playing out, right?
yeah, true. Yeah. So at this moment there is offloading here,
Yeah.
and there is a guy who's walking there, and he's not really aware of the thing that's going to happen.
Yeah.
So at a certain time, there is going to be an alarm, and you will probably hear like, "Hey, there's something going to happen at the moment," or at least there should be an alarm as well. And this is the moment that he's going to actually notice it. You see that he's a bit scared. Then he's going to
Yeah.
walk away quite slowly, I would say. I would start to run. And this looks a bit as if it were LNG. Yeah, so that is not super toxic, but of course, I wouldn't
Yeah.
want to
There it
breathe in,
goes. Yeah.
I said, large quantities. So within a
Yeah.
couple of seconds, things are closing off. And then, um, the ship is either drifting away or the loading arms are pulling back. I can't really say
Yeah.
for certain. Yeah, and what you see is that there is still a small amount of LNG, so in this case, in between the two valves, but in principle, that shouldn't be an issue too
Yeah.
much.
Yeah.
Uh,
Yeah. Hey, and what type of valve are we talking about? Is there a typical valve type that is always used in these
these kinds,
perks?
in my experience, I've usually seen the ball valves here.
Right.
Yeah. because a ball valve is quite easy to turn. If you would have a butterfly valve, you would need a bit bigger forces.
Yeah. All right. Maybe you can introduce us to the let's say the scenarios that we're going to discuss further, Mick.
Yeah. Okay, sure. Yeah. So what we're going to talk about here is during the ship offloading. So you're loading towards the tank. We're going to look at what are the typical risks when you close a valve at the tank itself, and what are the typical risks if you close the perk or the emergency shutdown valve.
Yeah.
Those are two words which are used interchangeably quite often. So first we're going to look at what happens when you close a valve at the tank. So here in this case, here you have a bit more control typically of how long you're going to close it, or how long your closing time is, because if you close a valve here, then it is typically it's part of a process that you say, okay, I think we are nearing a high load of the tank. We can start closing it off.
Yeah, so it's not related to the ship drifting off. There's no emergency at play.
Yeah, typically not. Typically not. You could actually close it here too, as a side benefit of closing the other valve. But in this case, typically it is not. And the things what you have here is as I told earlier. So you have a flow which is moving into the valve, which is closing. Well, at the downstream side, you have a tank pressure, so you will not see any change in pressure because a pressure information which is traveling at 1,000 meters a second towards a valve which is a couple of meters away, that's going to keep the pressure downstream more or less constant. And that's just the hydrostatic head of the liquid inside my tank here. But the pressure from the ship, you have a 2-kilometer line. So if you start closing the valve, it takes 4 seconds for the pressure information to travel from here towards my ship and then back again. So I could close a valve like this within 3 seconds, then I would not have the first information of the valve closing having traveled fully back to my closing valve. So So
for this,
please do ask a question.
So for this, if that valve is closed, I guess what you're saying is that the upstream pressures upstream of the valve, are most relevant to look at. I mean, everything downstream just matches out with the level, the static head of the tank.
Yeah, true. So there's a piping system that has a design pressure, and you want to be sure that if you close the valve, that you don't have pressures which are above a certain value above your design pressure. Typically, you can allow for slightly higher pressures because it is an occasional load, as they say. But it's the main concern in this case.
Yeah, let's also give an time. Let's focus on that valve, that ESD valve. Maybe in the next slide, you can introduce it a little bit, Mick, and then we jump to the actual analysis of the system, I guess.
Yeah, sure. So the other thing here is so here is again an image of a loading arm. In this case, the flow is going the other way. There is a flow into the valve, but that is quite close to a ship where you also have a fixed pressure. So that means that the pressure upstream, that means at the ship side, is going to be more or less constant during the ESD closure. However, when you close this, you limit the flow, and typically you will get a slightly higher pressure because a pump is able to deliver higher pressures when the flow is lower. And that is something that you have to take into account. However, on the downstream side, there is a huge column of liquid which is traveling away, and you're trying to pull on that liquid in order to stop it. And then typically you start running into issues, which we're going to talk about later.
Yeah. So just to summarize, like when we're looking at this valve closing, this is the emergency shutdown valve in that loading arm. Like the most important aspect to look at is the downstream side of the valve, if I understood you correctly, because there is where a long column, let's say on the land, pulls on the liquid because it's still moving.
Yeah. Cool. Then we can talk a little bit about how that looks like. So how does the pressure typically behave in a piping system? So we have some kind of a probe where we can measure pressure over time, and we can look at what that would typically look like. So first we can, so here is the loading arm from which the liquid is flowing into your system.
Okay, so what is land and what is ship side?
Land is the upper right side, and the ship side is from the location of the arrow. And so the ESD closed. Here's the ESD. We don't see our loading arm. It wasn't part, say, in this model. So, and what we can talk about here is, okay, what does the pressure response look like? And first, we're going to look at what would happen if you would be able to have negative pressures in a line. It's not really possible, but so liquid. So if you were to be able to have negative bar pressure in a line, and that would be the line in red that you see over here. So here you see the pressure in bar. You start out at a given steady state pressure. That's the pressure that you need to get your liquid all the way, let's say, on land into a tank somewhere. So you have a bit of
like 3 bar of let's say pump discharge pressure from the boat.
Yeah. It's a little bit low. Typically you see values of 6 bar, something like that. But in this case it is 3 bar. And what you see is that if you were able to pull on the flow, that means if the pressures could be negative, then you would see a drop in pressure, and then over time you would get a kind of oscillation of just pressure waves going back and forth, but the flow being more or less steady. Yes.
Why is that? Like, maybe you can elaborate a little bit on the red line first. So just to summarize, we got the pump discharging at 3 bars in this image. At what time does the ESD close, for example?
So in this case, you would expect the ESD to close more or less here. So,
and then a couple seconds of closure time.
Yeah, well, I think here it was closed, or it started closing from, say, 0. And you see in the beginning a slight lowering of pressure that would be coinciding with a slight lowering of the flow rate too. But usually at the beginning of the closing of a valve, there isn't that much response by the flow, because the pressure drop hardly has an effect. Only when the valve is really starting to close will you see a real effect on the pressure drop.
Oh, so that's like very non-linear, the actual, let's say friction that the valve brings.
Yeah. And so essentially in the beginning, you have a hole like this, and you can close it a little bit, but it's still quite a big hole. And only when the hole really starts to close is where you see a sharp reduction in the possibility of the flow going through that the hole. So
and
so
why?
you see,
sorry, go ahead.
So in the beginning, you will see only a shallow reduction, very minor, of the pressure. And when it starts to close, the last 30%, and that's a typical value also, 30% of the valve closure is the effective closure time of a valve. And that's
Right.
it's almost for each for all valves the case.
Yeah.
And there you see a sharp reduction, and when it is 100% closed, only then uh, uh, there's also
Yeah.
there's a couple of things actually happening. The valve is closing. There's also new information coming from the tank that is increasing the pressure. So I can't
Yeah.
say 100% if it closed at 10 seconds or a bit later. It depends
Yeah.
a bit on the pressure information coming back. But
Yeah.
afterwards,
Yeah.
your pressure is going to be say oscillating at a positive value again.
Why is it oscillating? Why is it not just dampened out by the elevation in the tank?
The thing with the oscillation is that you have you y- it's a bit like a spring. If you try to stop a spring in an instant,
Yeah. Yeah.
you
Yeah.
will stop it, but it will keep on bouncing, and it will go
Yeah.
back and forth, back and forth, back and forth, and then after some time, friction is going to take away that
Yeah. Yeah.
say that effect. But here, the flow rates are nearly zero, so that means that the pressure drop is also very low. So
Yeah.
you see, you don't really see dampening happening here. But
Yeah.
this is not what really happens. Yeah, this is what happens if you would have a very high initial pressure. If you would elevate all the
Right.
pressure in the system, you may be able to have a response like that in the system. But it's not what you have, because there is an absolute limit to which you can bring a liquid,
Yeah.
a lower limit. And if you bring the pressure in that liquid to a value that is equal to its vapor pressure, it starts to evaporate.
Yeah.
Even though
Yeah.
you don't heat it up,
Yeah.
you can still make it evaporate. So if you're transporting water and you bring it to minus 1 bar or minus 0.99 something bar, it will start to turn into steam. It's called steam,
Yeah.
but it is steam nonetheless. And that is cavitation, actually.
Yeah.
That, yeah.
And so like I remember it to be like the way I always thought of it is that it is you boil something not by heating it up but by reducing the pressure.
Oh, yeah, yeah.
Yeah.
It is really boiling, and it is what you see. You saw it a little bit at the loading arm decoupling. Yeah, there it's really boiling, by the way, because it's boiling due to the heat of the
Yeah.
environment. But
Yeah.
so here inside, it would start to boil without adding heat.
Yeah. Yeah. All right. That's, I guess, a good bridge towards the black
Black line,
graph,
yeah,
black
yeah,
line.
true. So what you see here is as soon as the pressure at this point is going to drop below the vapor pressure, it
Yeah.
cannot really drop below, so it will start to evaporate. And what you will see at high points in your system, you will start to pull a vapor cavity. So the liquid, which is downstream of your high section, it's still going to continue, but here you will have a pocket of cold steam,
Why
essentially,
there?
because that's where the pressure is the lowest. At the highest point, the
Right.
lowest
Yeah.
pressures occur. Yeah.
Yeah.
So it takes some time before the pressure that is at the tank and the pressure that is here. So if the pressure drops, you will have a pressure gradient trying to stop the liquid column, which has an initial velocity,
Yeah.
usually because you go into a tank which has a high liquid level.
Yeah.
So there's going to be a pressure which is um, pushing it back or trying to deaccelerate the let's say liquid column.
Yeah.
This is what you see over here. So initially, you will have a liquid column which is traveling towards my tank, but my tank is actually pushing back.
Yeah.
That is decelerating my liquid column. After a time, it will start to flow back, but there is still a cavity here. And
Yeah.
then as it has flowed back completely into my cavity, then you will have an implosion of that cavity, and that's this sharp pressure rise that you see over here.
Yeah. Right.
Yeah,
Let me understand. Let me just make sure I get that completely and summarize that a little bit. So
sure. Yeah.
the pressure drops as the valve closes. It takes some time for all that information to come to the point where, in that let's say high elevation section of the piping.
Mhm.
And then because it's boiling, the pressure is the same. Like it's very flat line first.
Yeah, yeah. Yeah, the pressure there is constant because at a certain temperature in the line, yeah, the cavity pressure is going to remain constant. So
Yeah.
as the liquid is flowing back, it is flowing into a cavity, and as soon as it increases the pressure a little bit, it starts to, yes, it turn into liquid again. So
Yeah.
you're not really compressing a gas, you're just compressing into a thing that immediately becomes a liquid as soon as you try to compress it. So that's why
Yeah.
you,
Yeah.
yeah, you keep
It's
the
fascinating.
pressure constant.
Yeah. And
And
so
so that's,
you have a gas pocket in that elevated section, no liquid but gas.
yeah,
Um, and then where exactly what physically happens to explain that peak?
yeah, yeah. So the peak, yeah, that's real Waterhammer. Yeah, so what's happening is that on one side, yeah, you have a still standing liquid. So on the left side, because there is a closed valve, so liquid is going to be still.
Yeah.
I'm going to go back one slide because then I can, yeah, point at it a bit better. So this is zero flow. Here you will
Mhm.
have, yes, at this stage, just before the implosion, you will have a liquid column moving back, and as soon as as it has eaten up the cavity,
The
like
gas.
Pac-Man, yeah, the
Yeah.
gas, it has nowhere to go, so it hits the still standing liquid,
Yeah.
and that impact,
Like two water
depending,
fronts hitting each other.
two water fronts hitting each other, and
Or
normally,
water liquid fronts, sorry.
yeah, liquid fronts,
Yeah.
yeah, can be LNG or ammonia, or some other kind
Yeah.
of liquid, but yeah, so indeed, and that hits the other front, yeah, and then it has no way to go, and then, yeah, if you bang something, there's going to be a force. Well, yeah, here you have a similar, let's say, similar mechanism, and the peak
Yeah.
of that force depends on, yeah, on how quickly, yeah, the pressure information can travel actually, and on the density. So the higher the density, the bigger the force is going to be. The bigger the wave speed, the
Yeah.
higher the force is going to be. I'm not going to go into why that is exactly, but there are
Yeah.
perfectly, yeah, good reasons for that actually.
Yeah. Yeah.
I think
Yeah, go ahead.
we have to continue, right? Because we are quite well into our presentation already.
Yeah, so like
Uh,
like I just want to say like we're 45 minutes in, but let's take
yeah,
another 15 minutes, just to I know we've got a couple more slides and an interesting conversation going.
yeah,
So let's continue for now. If any if questions from the audience come in, I'll bring them forward. One question I have about these peaks, like when doing analyses on material stresses, pipe stress, flexibility analysis, there's a very strong link towards the piping codes. Same for pressure vessel design. How do the industry standards, maybe ASME or the European norms, or any other bodies, do they mention these, and how do you know if that peak is acceptable or not, because it's quite substantially higher than the steady state, let's say, pressures in the system?
yeah, yeah. So if you look at piping, there are limits. You can talk about occasional stress limits, but those relate to pressure as well. So if you do a stress analysis according to an ASME P31.3 or an EN 13480 European context, yeah, piping study,
Yeah.
yeah, there you have some increased limits for temporary loads, and this is a very temporary load indeed.
Mm.
But how specifically they relate to search problems. That is not really clearly stated. So these standards,
All right.
they do mention that you have to look at Waterhammer. There has to be an assessment. It doesn't state how you have to do it or what kind of limits or what kind of scenarios have to be considered. This is really something that is up to the engineer to decide what kind of analysis is appropriate in this case, or what kind of scenarios you have to look at.
Yeah. Do
Yeah.
they specify for which systems it has to be used? For example, a minimum length or flow rate or like anything?
No. It just has to be assessed. And yeah, indeed, a long line is more at risk than a short line.
Yeah.
And that's the main thing. Yeah.
All right. We got one question from the audience from Ahmed. Ahmed, first of all, thanks for submitting your question. The question, Mick, is why is the frequency of the hypothetical red line different than that of the real quote unquote black line?
All right.
In other
Yeah.
words, there are 2 peaks in the black line, but 9 in the red line. Like, can you elaborate?
Yeah, sure. The peaks in the red line have to do with how quickly the information goes from the valve closing and the tank. Yeah. So in this case, peak to peak, you can see that there is 3 or 4 seconds maybe. So indeed, the 4 seconds that we talked about earlier, if you have a 2-kilometer long line, 1,000 meters a second. And so this is only pressure information going back and forth. And what you see here is not necessarily the information of pressure only going back and forth, but that's the actual separation of the liquid, moving of the liquid, decelerating of the liquid, and then impacting again, and then having a new one. So the width of this line here, that is more or less half of this frequency. So in that sense, they are related. But the frequency, yeah, the whole event is just different. So the thing that
Different
is,
physics. Yeah.
it's really different physics from these peaks. So the width of these is related, but how many there are and how quickly they are, that really depends on the initial velocity that is there. It doesn't really depend on the wave speed necessarily. So yeah.
Why is there a second peak in the first place, Mick?
Yeah. So what happens in a line like this? You have the first cavitation, which is occurring here in the high point. And in this case, I'm going to go back to a couple of slides that we have earlier. So yeah, we had the first cavity occurring here. So what happened is that you close the ESD valve quickly.
Yeah.
You will get a cavitation here. That means that the liquid keeps on moving initially, even though here the liquid has stopped. Then the pressure from the tank allows it to reverse, flow into the cavity, and you get the high pressure peak here. Okay, the high pressure peak makes, first it stops the liquid, then you have a pressure wave stopping all the liquid here. But if you have a high pressure at this location, when it arrives at the valve, it wants to flow into the tank.
Right.
So the high pressure
it starts pulling again.
makes it move in the tank. Then you have a pressure wave of the tank pressure moving here, but now it becomes a flow changing wave. And then you suddenly have a flow again in that direction. And as soon as that arrives at this location, you will have a new cavitation bubble because you have a flow in that direction, which it can't. So at the high point, it starts to separate again. And that process keeps on repeating, and pressure drop over time makes these things shorter together in time, and also lower pressure peaks, just because the velocity is removed and the potential for pressure also reduces with that.
The energy dissipates.
Yeah,
Hmm.
it is a bit of a difficult process, but I hope people follow.
Yeah, but that is interesting physics. Given the time, Mick, I suggest we jump to the final graph that we have,
Yeah.
and maybe share what is
Yeah,
shown
we
here.
talked a lot about this actually, yeah. So these things we have talked about. So with the reversal uh, of the flow, so I think that is quite clear. Maybe one thing that we can talk about is unbalanced forces.
Yeah, so let me circle back just to that one slide one back, Mick.
Yeah, yeah,
Is like what I think, like, reason for me to bring this one up real quick is in this one, in the blue line, as far as I understood, you actually see the cavity size. I think that could be instructive.
yeah, yeah. True,
That's
true.
what I at least found interesting when you explained this to me recently. But one of the main questions I want to ask you about this image is, like, it shows also, especially with that red line, which is the
Mhm.
fluid velocity. It's a bit of a turbulent process. I mean, it's not all straight clear blocks. Obviously, the
True.
physics
Yeah,
behind it doesn't allow it. Like, how
true.
accurate
Yeah.
is this compared to, let's say, real life, and how would you interpret these results, and what's your confidence in that?
That is a very is a good question, is a deep question too, and that all relates to how you model the cavitation. So when you look at the graph that we see here, if you see a graph like this, I would be really confident that the pressure that we see, so here in this case, we have had to change the units a little bit. So, but here you see a pressure peak, uh, and this pressure peak is quite wide. And that means that it is due to some kind of large scale cavitation that has imploded, and you have like a single line. And this looks really accurate. But yeah, you have sometimes where you have long horizontal stretches in which you have multiple cavitation pockets occurring, and these can interfere and locally collapse, and then you get really high and short pressure peaks. In those cases, I would say you have to take the results with a grain of sand, and then you
Yeah,
just have to say, okay, look, there is a risk for cavitation here.
yeah,
So it depends a bit on um, how the profile is of the thing that you are seeing, how accurate you have to perceive the results.
yeah,
So
yeah,
there are some kind of so what you see here, and perhaps that isn't the best. It's a bit hard to understand, but in a high line like this, there are multiple, say, elements. And I think what you see here is, the cavity size of a single element. In reality, there
yeah,
are multiple elements. And if you add all those cavity sizes together, then you would see a peak going up like this and then going down, a bit like a
yeah,
parabola,
yeah,
because it coincides also a bit more with the velocity line that you see over here.
yeah, yeah,
Yeah, and this, sharp gradients is typically because you have multiple of these bubbles, they are collapsing, and that generates a bit of variation. And so the first line is still quite smooth, but during the collapse here, you would have um, multiple elements which are imploding in your horizontal line.
yeah,
That it generates a bit of static, I would say.
yeah. Is
Um,
that tested? I mean, could you test it on a real line?
yeah, for certain. Yeah, for certain. So we have done, I think that's already in 2016,
All right.
in cooperation with Deltares. We studied the effect of rapid valve closure in a measuring rig that was here in the Netherlands. And
Yeah,
what we saw is that especially the first one or two pressure peaks, they were really spot on if you use tools like this. And then the progression of those, you saw that there were bigger differences.
yeah,
There were some effects of gas pockets which came out of the liquid due to its lowering in pressure, which
Yeah.
had a kind of dampening effect on pressure peaks later on. So there were multiple things going on here, which could actually be the case for real as well, but it's really hard to predict how much dissolved gas there is in the liquid, something
Yeah.
I say like that. But we saw that the initial effects, that they were really well captured, and usually the initial effects are the greatest.
Yeah, like those are the ones you want to capture to,
Yeah,
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 to decide if
the
you're
most
safe.
accuracy. Yeah, yeah,
Yeah, exactly.
true.
Yeah. All right. Before we move into unbalanced forces, one
Yeah,
question from the audience, and
yeah,
then we'll move into unbalanced forces and start wrapping it up. Given the fact that we've been going for a good hour now, Mick.
yeah.
One question from Fabio. Fabio, thanks for submitting your question. The question is: would you ever design a pressure safety valve (PSV) at that expansion loop location to release the air in that area? Maybe
Oh,
you can
the
comment on that.
question is to release the air at the location of the high point.
Correct.
Yeah. Well, if you would do that, yeah, it's not really air. It is just it is the evaporated gas of that liquid. So if it were naphtha, you would have naphtha gas. If it were LNG, you would have
Yeah, right.
a
Flammable
gas, have
stuff.
natural gas. It's also flammable gas, but you're not really going to push it away because as soon as you start pushing, it gets a liquid. So the pressure is not really increasing. So yeah, a pressure safety valve is not helping. Yeah, the only risk that you would have is that during the high pressure peak, it is going to open. But then, yeah, the high pressure peak has already happened. And usually pressure safety valves, they won't respond quickly enough in order to help dampen your pressure peak. So then you have a high peak already, and now you also have the issue of having to remove a highly flammable or toxic, I say toxic liquid um, from the location of the high point. So yeah, so unfortunately, having a pressure safety valve is not helping you reduce the pressure, or at least not the pressure peak. Maybe the duration of the peak can be limited, but yeah.
All right. Thanks for elaborating on that, Mick. Let's jump to the final slide related to unbalanced forces.
Yeah.
And maybe, for the final few minutes of this conversations, you can introduce the concept of unbalanced forces to the audience and explain where the force comes from.
Yeah. Okay, sure. Yeah, so what you see here is a high point in a system. The high point isn't necessarily an issue, but you see that there's a couple of, say, elbows too in this system.
Yeah.
And if you would have a static system, so just steady state, things are flowing 3 meters a second, there isn't anything happening, but there is a bit of pressure drop, perhaps in the line. What you will see is that the liquid will have a bit of shear forces, shear friction forces with the pipe. And those shear friction forces, they are the reason why you have pressure drop.
Right.
So in the static case, in steady state case, you will have a slight difference between the pressure between any two consecutive elbows. So in this case, the pressure which on the downstream side is a bit low,
Yeah.
and the pressure on the upstream side is a bit higher.
Yeah, so what you're talking about now, if I understand you correctly, is the pressure difference between, let's say, the left side and the right side of this this, let's say, pipe bridge
Yeah,
due to friction loss in the flow.
yeah, yeah. And so even though there is a pressure difference between these two elbows, there's also a friction force along the wall of the pipe, and these two, they are in balance. And so
Yeah,
even though there's a slightly higher pressure on one side, it isn't um, well pushing the pipe, let's say, in one direction.
yeah,
But what happens now if you close a valve somewhere, and let's assume that we have a valve which is on the right side here. If we close this valve, that means that we are transiently increasing our pressure from this side. And that high pressure information starts to flow, say, in that direction. If we go to the final case, the ultimate case, where we instantaneously close the valve, which is on the downstream, that means that upstream of that valve, we have an increase in pressure. And that increase in pressure, let's say millisecond after millisecond, is traveling in your pipe. And as soon as it hits the elbow here, you suddenly have a case where you have a high pressure on this elbow and a low pressure on the other elbow. And that generates a net force in the direction of the flow in this case. So if you arrive at a crime scene, I call it a root cause failure study, and you look at how did the pipe move? Well, if the pipe moved in that direction, that means that there was usually a kind of transient pressure effect where the initiation of the pressure was downstream of that point. Because you are generating a high pressure that moves through your system. Here you will see a downward force. Here you will see a short force towards the right. And here you will also see a short force, but then towards the other right in the longitudinal direction of the pipe. So,
but I mean
that is what an unbalanced force is in essence.
Even though, you mentioned 1,000 meters, like 1 kilometer per second, that pressure, high pressure that arrives in the first elbow, like a split, like only a short amount of time later, it is already at the other one as well.
Milliseconds.
Yeah, exactly.
But you will still have 10 or 20 milliseconds. What happens when you have a closure of a valve which is occurring within a second? Then you may have a lower force, but that is it has a higher duration. It depends a bit on the closure time and the initial velocity, how high your pressure differences between the two bends are going to be. And it goes pretty rapidly because in the case of the initial or the instantaneous valve closure, you can close a valve within a couple of milliseconds. You have initially 3 meters a second of flow. There is an equation by which you can calculate what the pressure potential is that you have in that flow. I'm not going to explain that, but in this case, it is about 3 million newtons per square meter. That is 30 bar. So you have a pressure potential of 30 bar if you have 3 meters a second for most flows and most piping systems. It can be a bit higher, can be a little bit lower. So about 30 bar pressure difference, you can imagine 3 million newtons per square meter. So if you have a pipe which has only half a square meter, or maybe even only a tenth of a square meter, you still have 300,000 newtons, for instance. Even though it's a short duration, it is really going to move your piping system. So
hammering on your piping system.
Hammering on your piping system, indeed.
Yeah, Waterhammer. Yeah. All right. Thanks for explaining, Mick. And I think that's. I mean, you mentioned, there's equations behind it. There's definitely, a lot of more physics behind it. Maybe we can quickly jump to me sharing my screen. Give me 1 second.
Sure.
There we go. If anybody in the audience would like to, I mean, we've been going for well over an hour, so we need to wrap it up. If anybody in the audience really wants to go deeper into this topic, there's a couple courses related to Waterhammer on the EngineeringTrainer platform. So if I just head over to the total course list and search for Waterhammer, you immediately see quite a few courses popping up. There's a few shorter ones, especially this one is worth looking into. Understanding Waterhammer Part 1. Part 2 is on the way, but this one is a deep dive into the different scenarios that are relevant. So valve closure is what we discussed to some degree today, but will be discussed in more depth in this course, including all the equations, pump trips, and also switchovers in process plants. And if you really want to go in depth and really want to do these analyses yourselves, a good course, which is, roughly 19 hours long, so much more comprehensive. And a course that also requires you to do the analyses yourself in a piece of software in BOSfluids is also available on EngineeringTrainer.com. And just make sure to use the discount promotion code that is available in the show notes below this video. Anybody who joined in for this session or watches the video in the coming period can click on that link, leave your email address, and you will receive that discount promotion in your inbox in no time. Let me just move the screen back to only the two of us, Mick. We'll leave it at this. Having said that, Mick, I want to thank you for making the time. I mean, I think it was a very interesting conversation, and we went, quite into the several details.
Yeah, true. I agree. It went very fast also, so that's a good sign.
Time flies when you're having fun. That's a good closure.
Yeah.
Let me also thank everybody who tuned in remotely. Thanks for making the time, and it's a great pleasure to know that what we do here at Engineering Trainer, together with our partners like Dynaflow Research Group, is relevant to you. And also make sure not only to use that discount promotion, but to check out the webinars that we have upcoming in the coming period. A lot of new things are happening. A lot of new things are coming your way on the platform. So either like us on YouTube, LinkedIn, or subscribe to our newsletters to stay up to date about content like this. Mick, have a great rest of your day, and thanks everybody for watching.